We're surrounded by this incredible force every single day. We can't see it, we can't touch it, but it powers literally everything in our modern lives. It's kind of like an invisible river flowing all around us through our walls into our devices. So in this explainer, we're going to pull back the curtain and actually map that river.
So what is this invisible river really? Well, the best way to get your head around electricity is to think of it exactly like water. Seriously, it has a flow, it has pressure pushing it, and sometimes it runs into obstacles. Let's break down exactly how that works.
First things first, let's talk about the flow itself. In our river analogy, this is pretty simple. It's just the water moving downstream. In the world of electricity, we have a name for that. We call it current.
And this isn't just some random analogy. The source material itself makes this exact same connection. We totally get the idea of a water current in a river, right? Well, an electric current is the exact same idea. It's just a flow of electric charge instead of a flow of water. Same principle, different stuff flowing.
Now the key word here is rate. It's not just that charges are moving, it's about how fast they're moving. How many charges are flowing past a certain point every single second. And in the metal wires that make up our grid, the little particles carrying that charge are called electrons.
So how do we measure this flow? We use a unit called the amp, or just amp for short. 1 amp means that 1 coulomb of charge is flowing past a point every second. And just to give you a little perspective, 1 coulomb is about 6 quintillion electrons. That is an unbelievable amount of flow.
Okay, so here's a fun little historical quirk for you. Way back when scientists first started studying electricity, they didn't know about electrons. They had to guess what was flowing, and they guessed it was a flow of positive charge, moving from the positive side of a battery to the negative. We still call that conventional current. But they guessed wrong. We now know it's actually tiny negative electrons flowing the other way, from negative to positive. You'll still see both in diagrams today, so it's a really good thing to know the difference.
All right, so if current is the flow, that brings up a pretty obvious question, right? What's making it flow? Water on a perfectly flat table isn't going to go anywhere. It needs a push, some kind of pressure.
And this quote just nails it. The source explains that just like water needs a slope or a pressure difference to get it moving through a pipe, electrons need an electric pressure difference to get them moving through a wire. And that push has a name. We call it potential difference, or much more commonly, voltage.
Now, there's a more formal technical definition about the energy needed to move a charge, but honestly, just thinking of voltage as electric pressure is the most intuitive way to get it. It's simple. More voltage means a stronger push, and a stronger push means more current can flow.
We measure this electric pressure in volts, named for Alessandro Volta, the guy who invented the first electric battery. So the next time you see a 9-volt battery, you'll know exactly what that means. It's a measure of how much push that battery can give to the electrons in a circuit.
Okay, so we've got the flow, which is the current, and we've got the push, which is the voltage. But is the path for that river always perfectly clear and open? Of course not. In any real river, you've got rocks, you've got narrow spots, you've got things that slow the water down. And that brings us to our third big concept.
This is the question that unlocks the last piece of the puzzle. In any real-world circuit, the flow of those electrons is never perfectly free. There's always something getting in the way, some kind of friction.
And that opposition is called resistance. You can think of it as electrical friction. As the electrons try to move through a wire, they bump into and are attracted by the atoms of the wire itself. In our water pipe analogy, this would be like making the pipe much narrower, or maybe even filling it with a bunch of sand. It just makes it a whole lot harder for the water to flow through. The unit we use for resistance is the ohm, which is represented by that Greek letter omega. And I love its definition because it ties everything we've learned together so perfectly. 1 ohm is the exact amount of resistance that will let 1 amp of current flow when it's being pushed by 1 volt of pressure. See? It all connects.
So what makes something have high or low resistance? Well, the source points out 3 main things. First, how long the wire is. A longer wire has more resistance, just like a super long hose has more friction than a short one. Second is the thickness. A thicker wire has less resistance. It's like a wider pipe that gives the current more room to flow. And finally, and this is a big one, the material the wire is made of. And let me tell you, the material makes a massive difference. Here we're looking at something called resistivity, which is just a material's natural built-in resistance. Look at copper. It's a fantastic conductor, and its resistivity number is tiny, incredibly low. Now look at glass, an insulator. Its resistivity number is astronomical. It's gigantic. This is exactly why we make wires out of copper and then we wrap them in plastic or rubber. One lets the river flow and the other keeps it contained.
All right, we've got our three key players: current, the flow; voltage, the push; and resistance, the obstacle. Now, let's bring it all home with the one beautiful, simple rule that ties them all together.
It's called Ohm's law, and all it says is that voltage equals current times resistance. V equals I times R. This simple little formula is the absolute bedrock of electronics. It means if you know any two of those values, you can always figure out the third.
Let's put it to the test with an example from the source. Okay, we've got an electric heater. There are 60 volts of push behind it, and it's got 4 amps of current flowing through it. So, what's its resistance? Well, we just rearrange Ohm's law. Resistance equals voltage divided by current. 60 divided by 4 gives us 15 ohms. Easy enough. Now, what happens if we crank up the voltage to 120 volts? The heater's resistance doesn't change. It's still 15 ohms. So now the new current is 120 volts divided by 15 ohms, which gives us 8 amps. Double the push, and you get double the flow. It just works.
So, we've got the flow, the push, the obstacle, and this golden rule that connects them all. But why does this actually matter? Why is getting this so powerful?
Because it makes the invisible visible. It gives us a way to picture this force we can't see. Voltage, measured in volts, is the water pressure. Current, in amps, is how much water is flowing. And resistance, in ohms, is the friction or the narrow parts of the pipe. Every single electronic device you have is built on balancing these three things perfectly.
And that, really, is the whole idea. Now that you know the rules of this invisible river, the next time you plug something in or just flip on a light switch, I want you to take a second. Picture that flow, that pressure, and that resistance, all working together in perfect harmony, just to power your world.